Welcome to the recap for Lecture 8 of Formal Methods. Last time we introduced the propositional calculus. We gave this definition of a proposition, a declarative statement that is either true or false. And we defined what an axiom is. An axiom is a Boolean expression that defines the properties of Boolean operators. Axioms are never proved, they are assumed to be valid, in other words, true in all states. And then we defined what a theorem is, either 1, an axiom, or 2, a theorem that is proved equal to an axiom, or a previously proved theorem. All theorems are valid. Then we took a look at our very first axiom, the associativity of equivales, which says that you can put the parentheses around the first P equivales Q and then equivales R, and that's the same thing as putting the parentheses around Q equivales R and doing that first and then doing P equivales that. And we said that this axiom allows us to write a string of equivales, variables that are equivalent to each other, and either as we can put the parentheses wherever we want them. And then we looked at axiom 3.2. Again, this is an axiom. It is assumed to be true, so we don't prove it. And the symmetry axiom says P equivales Q equivales P. So you can put them in the P and the Q in any order. And we mentioned the fact that we can put the parentheses anywhere because of axiom 1. Because equivales is associative, we have our choice about where to put these parentheses. All right, and now what we are going to do is our first step in a big journey is we are going to start proving theorems from axioms. Now, the first theorem that we are going to prove is not a numbered theorem in the book. So we are going to use 3.1 and 3.2 to prove the following theorem. P equivales P equivales Q equivales Q. All right, and how do we do this? Well, here's how we do it. First of all, we write down what we're trying to prove, like we just did. And then we write down the word proof and underline it if you're doing this by hand, the word proof. And then we start with what we're trying to prove, and we have to get it to a previously proved theorem. So we start with P equivales P equivales Q equivals Q. And now what we need to do is we need to do a sequence of steps by which we transform this P equivales P equivals Q into a previously proved axiom or theorem. So here we go. Our first step is we outdent and put an equals, and then we indent and we put this angle bracket, which is called the hint. Inside the angle brackets is called the hint. And our hint in this particular proof step is 3.2. So what we are doing is we are using a previously proved theorem, namely 3.2. And we are choosing to put the parentheses around the first P equivales Q. So you see that in our hint 3.2, that's the same as the axiom that we have up above on the first line of the slide. And the key idea here is to identify the part of the hint that we have in our first line, in the first line of our proof. So look, in the first line of our proof, we have a P equivales Q. Okay, so do you see that? It's underlined in red. And then in the hint, we have P equivales Q. But in our hint, what does the hint say that P equivales Q, close parentheses, equals? Well, it equivales P. So what we do is we replace the P equivales Q with P as follows. Boom. So do you see what happened was, because the quantity in parentheses is equal to P, that means we can replace the P equals Q equals Q in the first line of the proof with P. And we wind up with P equals P. So that is, but now is that a previously proved theorem? No, it is not. So we have to do another step. So our next step is, we are going to use 3.2 again. And furthermore, we are still going to use the same grouping, P equals Q equals Q equals P, close parent equals P. But this time what we are doing is we are identifying the P with the first P of this line of the proof. So in this line of the proof we have P equals P, and so you see that red P in the next to the last line of this slide. Well, our hint says that that's that's equivalent to P equals Q equals Q. So what can we do? We can replace that P with the P equals Q equals Q and bring it down like that. And so now notice that what we've done is we have replaced the red P with the blue P equals Q, but we have to bring down this additional equals P. But now, sports fans, does this look familiar? P equals Q equals P? That is precisely 3.2. And so we have shown that the first line of our proof, P equals Q equals Q, is equivalent to P equals Q equals P. But that is a previously proved axiom or theorem. Namely, it's 3.2. Okay, so now our next axiom is an identity axiom. It is the identity of equivalence. So here is the concept in general. If star is a binary infix operator, the identity of star is the constant I such that x star I equals x. Now let's make sure that we understand the various parts of this definition of an identity. Okay. First of all, star is a Boolean infix operator, or it's a general infix operator, so it comes in between two operands. Now x, lowercase x, is a variable, and lowercase I is a constant. And if you have a constant I, such that if you do x star I and you get x, that means I is an identity element. By the way, this works the other way around too. I star x also equals x. So this is the concept in general, and here are some specific examples. The first one is the identity of multiplication. So 1 is the identity of multiplication because x times 1 equals x. Now notice that x is a variable and 1 is a constant, and because x times 1 equals x, that means that 1 is the identity of multiplication. So the star in this case is the multiplication operator, a binary infix operator. Okay, so you see how that works? Now what about addition? Well, 0 is the identity of addition because x plus 0 equals x. Here again, x is a variable, 0 is a constant, and because x plus 0 equals x, that means that 0 is the identity of addition. 3.3 says that true is the identity of equivalence. Now why is that? True is the identity of equivalence because P equals true equals P. So notice here that P is a variable, true is the constant, and the binary infix operator is equivalence. So P equals true equals P. Now this is slightly different from 3.3 because 3.3 has true equals Q. But here it looks like it's P equals true equals P. But we can swap the true and the equivals in 3.3 because of the symmetry axiom 3.2. If you have two Boolean variables or constants, then P equals Q is the same thing as Q equals P. In other words, you can swap them. So going back to our definition, 3.3 says that true equals Q, but it's possible for us to swap the true and the Q. So that would be Q equals true equals Q. And of course, if it's the same for Q, if what's true for Q is true for P. All right, now comes an amazing theorem. Notice that 3.4 is not an axiom. 3.4 is a theorem. And what is a theorem? The theorem is true. Now, when I first saw this, it blew me away, because what we're going to do is we're going to prove that true is true, in a sense. We are going to prove that true is valid in all states. It's a validity. You show this to a mathematician and he'll flip out. Okay, but this is a very elegant system, and true is a theorem in this system. So let's prove true. So now how do we do it? Well, we write down proof. If you're doing this by hand, you underline the word proof. Okay, and we start with true, and we have to get this to a previously proved axiom or theorem. Okay, so now how do we do this? Well, our first step is we're going to use 3.3 with P replaced by true. Now let's go back to 3.3 and see what 3.3 looks like with P replaced by true. So here is 3.3, and notice that if we do 3.3 with Q replaced by true, we get true equals true equals true. So notice here that in the hint, we have written down 3.3 with P replaced by true. So we have written down true equals true equals true. Now watch this. Do you see we have true on the first line of our proof? And in this hint, we have, what does true equal? Well, it equals true equals true. Are you with me? So therefore, what do? We replace that true in the first line of our proof with true equals true. Okay, so do you see how that works? With true equals true. And so now what is our next step? We're going to use 3.3 again. This time, we're going to use it in its form true equals Q equals Q. And how are we going to use it this time? Do you see that in this line of our proof that we have true equals true, and we are going to take that second true and we are going to replace it with Q equals Q, because 3.3 says that true equals Q equals Q. So what do? We bring down that first true equals, and then the true that's underlined in red, we replace that with, we substitute equals for equals, and we replace that with Q equals Q. Are you with me? Okay. But look, this is 3.3. True equals Q equals Q. So let's go back to 3.3 and check that. And sure enough, 3.3 is true equals Q equals Q. So we have proven true. We have proved true. Now let's go back and talk about the inference rules that we used in this proof. Okay, so let's start with this part of the proof and see how we executed this proof step. Now, do you remember that there are 4 inference rules that we use to prove? Inference rule substitution, inference rule Leibniz, inference rule equanimity, and inference rule transitivity. Okay, so do you see that inside this hint we use 3.3 with P replaced by true? Now what inference rule are we using to say 3.3 with P replaced by true? That we are using inference rule substitution. So what does inference rule substitution say? Let's go back to 3.3. Inference rule substitution says that if true equivalence Q is true in all states, then it is true with any variable replaced by any expression. That was inference rule substitution. So what we did is we replaced P with true. So because 3.3 is true, is valid, we can replace any variable with any expression. So that's how we got true equivalence true equivalence true. The way we got that was by inference rule substitution. And then what we did is we identified this true in the first line of our proof. And in the next step of the proof, what we did is we used Leibniz. We substituted equals for equals. In other words, because the red true is equal to the blue true equivalence true, we could substitute equals for equals and replace that red true with the blue true equivalence true. That was Leibniz. So do you see in this step we used inference rule substitution and inference rule Leibniz. Now when students first learn how to do proofs using this calculation logic, there are some common pitfalls that arise when you use textual substitution. And so here I've categorized some common mistakes. So what is textual substitution? In general, it's capital E is an expression, and the textual substitution square brackets. Inside the textual substitution square brackets, we have a variable is replaced by an expression. And the key idea that students frequently misunderstand is that lowercase z must be a variable. Okay, remember the uppercase letters are expressions, Boolean expressions, and the lowercase letters are variables, and that z is replaced by f, that z must be a variable. So here are 4 examples. First of all, what about this textual substitution? Is it legal or illegal? Well, E is an expression. Q is a variable, and so we can do Q is replaced by true. So this is legal because Q is a variable. In fact, this is the precise step that we did in the previous proof. Let's go back and look. You see, the expression was theorem 3.3, and the textual substitution was P was replaced by true. Okay, but now how about this next one? Suppose you tried to do this. E with true replaced by Q. Is this legal or not? It's illegal because true is not a variable. What is true? True is a constant. Students sometimes try to do this. They try to replace true with something. But that is illegal because true is not a variable. All right, so here is the next example. Suppose we have a textual substitution like this. E is the expression and Q is replaced by Q and P. Is this legal or illegal? All right, so this one's legal because here again Q is a variable, and in this case the expression F, capital F, is the Boolean expression Q and P. But watch this. What about this? Is this legal? Well, you might think, well, Q is a variable and P is a variable, but no, this is not legal because it's not a single, because that and in there, this is an expression, okay? So the problem is Q and P is not a variable. Are you with me? So this one is illegal. All right, so these are some common pitfalls that you need to learn when you're first learning this, that you need to remember when you are first learning how to do these proofs. Okay, so always keep this in mind, these examples in mind. All right, so we've done 3.1, 3.2, 3.3, 3.4. We've discussed those. We proved a few theorems. 3.5 is reflexivity of equivales. That's P equivales P. All right, and here is the next group of axioms and theorems. This section is negation, inequivalence, and false. So 3.8 is the definition of false, which is false equivales not true. 3.9 is, oh, by the way, the word definition is the same thing as the word axiom. A definition and an axiom are both assumed to be true. So sometimes we call them definitions, sometimes we call them axioms. It's kind of a matter of style, which one we use. 3.9 is an axiom, distributivity of negation over equivales. This is an interesting one. If you have a negation in front of parentheses with P equivales Q, that negation goes to the first one. That it doesn't go to the second one also. It distributes. It only you can get rid of the parentheses by having that negation go to the first variable in the expression P equivales Q. And again, this is an axiom, so it's not proved, it's assumed. 3.10 is the definition of inequivalence, and it says that P is not equivalent to Q, is equivalent to not parentheses P equivales Q. 3.11 is not P equivales Q equivals P equivals not Q. Now this is a theorem that can be proved. It's not assumed. It can be proved from the previous axioms or theorems. 3.12 is double negation, not P equivales P. All right, so that's obviously why it's called double negation. And again, this is not an axiom. You can prove this 3.12 from 3.11, 10, 9, and so on up to the first one. 3.13 is negation of false, not false equivales true. 3.14 is the quantity P not equivalent Q is equivalent to not P equivales Q. 3.15 is not P equivales false. 3.16 is the symmetry of inequivalence. 3.17 is the associativity of inequivalence. 3.18 is mutual associativity. 3.19 is mutual interchangeability. And 3.19.1, now this extra 0.1 means that this is a theorem that is not in our textbook, but or it's in the textbook and it's not numbered. So as we go through and learn all these theorems, there are some extra ones that are not in the book that I have included in the list of the ones that we need to know, that we need to learn. Now, I think your homework assignment for next time is going to be to prove 3.12 double negation, 3.13 negation of false, 3.14 P is not equal to Q, quantity equivales not P equivales Q, and 3.19 mutual interchangeability. Okay, so good luck with that, and see you next time.